At the end of the previous lecture, on Friday, we started with the metric tensor. We review the main points, and then we go beyond that. So what was the physical motivation for the metric tensor? The idea was that in Minkowski space, in inertial Cartesian coordinates, the distance squared, the invariant distance squared between two events with coordinates x and x hat are given by this expression here. And that can be captured nicely with this matrix eta mu nu. Now, remember that even on Minkowski space, we can have a non-trivial metric. Because even on Minkowski space, when there's no curvature at all, we can always choose coordinates other than inertial Cartesian coordinates. You could choose polar coordinates, or cylindrical coordinates, spherical coordinates of various kinds, and also accelerated coordinate systems. And when we do that, then the invariant distance squared between two nearby points is not going to take that simple form, but instead it's going to be more complicated. It's going to look like this. The invariant distance squared is going to start out quadratically, because it's a distance squared. It's going to start out quadratically, but with a matrix that will be, in general, very complicated, not at all like that. And there will be higher order terms. But in particular, if you just go to second order, then this is what you get. For the distance between 2 points, even on flat space-time, just by going into an arbitrary coordinate system. How do we recognize, if you're given a g mu nu of x, how do you recognize whether or not this is describing Minkowski space or a curved space-time? Well, if it is Minkowski space, then there must exist a change of coordinates such that the g mu nu of x in the new coordinate simply becomes this constant matrix. Right? But in practice, it's very hard actually to determine that. You're given a g mu nu of x, and then you're asked to find whether or not a change of coordinates exists such that this transforms into that. That can be a little tricky to do. Anyway, that's what you would have to do. Now, historically, the generalization that the way that Einstein went from special to general relativity is to say that, well, okay, so the metric doesn't really have to look like this in special relativity. It could also look like that if you allow for arbitrary coordinate systems. However, you still recognize that it is special relativity by the fact that there always are changes of coordinates such that this becomes that everywhere. And Einstein said, well, what if we allow more general g mu nus of x? Much more general ones. G mu nu of x's that don't have changes of coordinates that would transform them into this globally. And instead, he required only the g mu nu of x can be made to look like this at a point. At every point, for every point there ought to exist coordinate systems such that in the neighborhood it looks like that. But the main breakthrough was that he allowed g mu nu of x that do not arise from eta by a change of coordinates. But other than that, everything stays the same. So historically, Einstein allowed g mu nu of x's which in no coordinate system are this for all x. They may be this for some x, or they may not even be that for any x. And this goes way beyond special relativity then. But he couldn't allow arbitrary g mu nu of x's. He had to implement his equivalence principle. Equivalence principle being that the g mu nu of x have to be such that for any point you pick, there's a coordinate system that transforms this into the eta matrix at that point. Now, at the end of the previous lecture, somebody suggested that I give you a quick review of the equivalence principles. So I added this here. Remember, there's more than just one equivalence principle. There's the weak equivalence principle, and it says that freely falling small masses all fall the same way. So whether there's a feather or there is a kilogram weight made out of steel, they all fall the same on the moon. Okay, that's the weak equivalence principle. Einstein required more than that. Einstein required that the physics of the feather and the physics of this 1 kilogram weight is the same. That the internal physics of those objects is the same. So he asked that special relativity and all the laws of nature that go along with that hold for freely falling systems with all the trimmings. They don't just fall the same, they have the same physics in there. And then there's also a strong equivalence principle, and that requires even more. It requires that not only is the same physics holding for the feather and for the kilogram piece of iron, but also the same gravitational physics is supposed to hold there. It's not just the standard model of particle physics that ought to be the same special relativistic model for the feather as it is for the piece of weight, but also the gravitational physics ought to be the same. It turns out that that is a more restrictive condition indeed, and it rules out certain fifth force alternatives to general relativity. You could have Einstein's equivalence principle with a more general gravitational theory, but not with the strong equivalence principle. Strong equivalence principle comes in, for example, when you consider stars and planets, whose physics is fundamentally also determined by gravitational interaction among themselves. The planet itself is strongly shaped by gravity, whereas a feather is not really shaped by the gravity of one part of the feather onto another part of the feather. So when Einstein required that the g mu nu of x are arbitrary, except that they have to fulfill the condition that there must always be a coordinate system, such that at a given point the g mu nu is the eta, he really required that the physics is the physics of special relativity when you are in a suitable coordinate system near to a point that you choose. So if you pick out a particular point on the space-time manifold, a particular event, then there's always a coordinate system, and that will be the coordinate system of a freely falling observer, for which special relativity holds there. The masses have to be small, the coordinate systems have to be small, because as soon as you make them larger than second order in distances, tidal forces will be noticeable. And as soon as there are tidal forces, you can tell the difference between gravity and acceleration. Because if you're in a rocket and you're just accelerated in a rocket, there are no tidal forces. The acceleration exerts the same force on all parts of you. Whereas if you are exposed to a gravitational field of the Earth, for example, then strictly speaking, different parts of you may have a different distance to the center of the Earth and therefore experience different gravity. And therefore fall differently. So what was the mathematical description then of the metric tensor? So the physics was that we use it to calculate up to second order distances, and that can be integrated up, of course, then. So infinitesimal distances. But mathematically, we described the metric tensor as a covariant tensor of rank 0, 2. It's covariant, that's why it's a 0 here, and it's of rank 2. And strictly speaking, because of Einstein's equivalence principle, this is because Einstein wanted special relativity to hold in freely falling coordinate systems that you can always, rectangular coordinate systems that you can always build around any event. And eta is a covariant tensor of rank 0, 2 in special relativity, so it has to be that in general relativity as well. Just a preview, later on we will see that we will use Einstein's equivalence principle several times. When we wonder what is the equation of motion of this or of that, in curved space-time, we will often use Einstein's equivalence principle by going into an adapted coordinate system. It will turn out to be called the Riemann normal coordinate system about an event. Then to lowest order, special relativity must hold. That's the equivalence principle. Then we can write down the equations, and then we can generalize them in a uniquely in a covariant way to general relativity. So here, similarly, the eta is uniquely generalized to G. So now, let's say we have n cotangent vector fields, theta mu of x. And so for each theta, for each mu, this is a cotangent vector field. And let's say we choose them in such a way that they are not linearly dependent of each other anywhere, which means that at every point x, they form a basis of the cotangent space. Okay, so at every point x, the set of them forms a basis. This is a basis-valued function here, if you like. So if we have those basis vectors in the cotangent space, then our metric must be expandable in that basis. So there must be coefficient functions, g mu nu of x, such that this equation holds. Whatever we might choose for those theta mu of x, we could choose them to be the dx mu that are associated with a particular coordinate system, but we don't have to. Now, we said that the g mu nu of x is invertible. That is because the metric tensor is non-degenerate. And that means that there exists a tensor, which we will call G inverse, of rank 2, 0, which is a twofold contravariant tensor. The G inverse is given by the inverse matrix here, and then it is expanded in the dual basis, the basis dual to the theta in the tangent space. And then it's a little exercise to show that this thing really is that these are really the coefficients of a twofold contravariant vector, a tensor, if these are the coefficients of a twofold covariant tensor because of that relationship between the two of them. In general, here and in the future in this course, whenever we raise or lower indices, in principle, we're going from one tensor to another tensor of a different type even. So we should really use other names for those. But as a general convention, whenever we raise or lower indices, we will keep the name the same. So for example, the Riemann curvature tensor later on, we will always call it R, no matter where the position is of its indices. But in principle, these are different tensors, and it is for convenience that we keep the name. So now that we've allowed ourselves an arbitrary choice of basis in the cotangent space, and therefore also in the tensor space, in the space of covariant two tensors, now that we've allowed ourselves an arbitrary choice there, we can reformulate in a more modern way what Einstein's equivalence principle is. We can reformulate in a more modern way what Einstein's requirement on the metric tensor was. Remember that originally, Einstein had said, we ask that for every point of the manifold, there exists a coordinate system, so that when we choose these bases for the cotangent and tangent space, then the metric tensor takes this form with, this is the metric tensor. This is it explicitly in that basis, such that the coefficient function takes the value of the matrix eta mu nu at the point P. Okay, so that was originally the requirement. For any point you may choose on the manifold, there has to exist a coordinate system, and those will be the coordinates of a freely falling observer. There has to exist a coordinate system such that the associated basis, canonical basis that comes with the coordinate system, will make the coefficient matrix of our metric tensor take that form at the point P. But you see, what this means is, in other words, that we require that for every point P in the manifold, there exists a basis in the tangent space, in the cotangent space, a basis of dxi, where they stem from a choice of coordinate system, but never mind that. The point is there exists a basis in the cotangent space, such that in that basis, the metric tensor takes this form. Okay? You see that? It's a subtle distinction. If this is true, that requirement, then it means that at every point of the manifold, there exists a basis, namely this one, for which the metric tensor takes that form. But this means that we can now express Einstein's equivalence principle also this way. Independently of any choice of coordinate system, we don't even need to talk about coordinate systems. We require that there are choices of dual bases, theta and E, such that the metric tensor in that choice of bases has as its coefficient functions simply the matrix eta mu nu, a constant, for all P, at all points of the manifold. If you want to know, well, at a particular point, how do I know which basis I have to choose such that this is true? Well, just find a coordinate system for which this is true and read off what the basis vectors are, those guys. And then call those dxi the thetas. And then for another point, you need other coordinate system, other dxi's, and call them the thetas, and so on. So you can piece together all the thetas. So you harvest, so to speak, the diagonalizing bases from all those many coordinate systems that do the trick of making this true at a point. And then you collect all those special bases, collect them in this, the theta mu of x. This is the collection of all those diagonalizing bases for those cotangent spaces. And with that collection of bases, with this basis valued function, you then have that the metric tensor has a coefficient function, which is always this. Now the metric tensor looks trivial and there's no information in writing it down, but now all the information is encoded in this basis valued function. We will say much more about this, discuss much more about this later on. Okay, so now knowing distances, being able to calculate distances, at least infinitesimal ones, we've done that so far, a distance square between infinitesimally separated points. What else can we do now with the metric? What does knowing the metric allow us to do that we couldn't do before? But first of all, knowing the metric tensor will allow us to get a canonical volume form associated with that, which is quite obvious. Once you can get lengths, you should be able to calculate volumes. A volume form, if you remember, was a n form whose coefficient function is always positive. Then the second point, I'm sure most of you are very familiar with that. The second point is that you can use the metric to raise and lower indices. Technically, it means that the metric tensor provides a map from the tangent space in the cotangent space and vice versa. But we can do much more with that. Now that we have the metric, we can define the D'Alembert and Laplace operators in a covariant way without referring to coordinate systems. And we can define the Laplace and D'Alembert operators not only on functions, but we can define them also on arbitrary differential forms. For example, well, that would be nice. For example, we can write then down a wave equation for, if you want to, for 3 forms, because we have a D'Alembert operator that acts on 3 forms. Now, for that purpose, we first need to introduce the so-called Hodge-Star operator. The Hodge-Star operator will map p forms into n minus p forms. And then once we have that star operator, we can turn the space of differential forms into a Hilbert space. Well, not always. It depends on the signature of the metric. But for Riemannian manifolds, it's a Hilbert space. And then, with respect to that inner product, it's always an inner product space, not necessarily a Hilbert space. Once we have this inner product on the space of differential forms, then we can define the adjoint operator to the exterior derivative, and that will be the co-derivative, yet another derivative, as if we hadn't had enough yet. This one is, however, not a derivation. It's a derivative, but it's not a derivation. It doesn't obey a nice Leibniz rule. And that's because it is decorated with the metric. The metric goes into this. Remember that the exterior derivative can be defined, as we did, without any knowledge of the metric. But the co-derivative will have knowledge of the metric. So we define the co-derivative, and then once we have the exterior derivative and its adjoint, the co-derivative, then we can define the Laplace and D'Alembert operators, which will be second derivative operators that map p forms into p forms. And once we have them, well, then we can write down wave equations, such as the Klein-Gordon equation. And we can also study then the Maxwell equations, for example. And we will find out that, for example, the Maxwell equations partially can be formulated without knowledge of the metric, and some other Maxwell equations require the metric. So let's start with the fact that the metric will induce a volume form. The proposition is that given the metric G, this induces a volume form omega, that is to say, a positive n form. Let's assume, as always, that our manifold is oriented, and we consider a positive chart. Remember that if it's oriented, it has an atlas that covers it, and the change of coordinate maps will have Jacobi determinants that are all positive. And relative to that atlas, our chart is positive. Then, in such a chart, we define the volume form that is induced by the metric as a square root of determinant of G, square root of the absolute value of the determinant of G, times dx1, veg dx2, etc., up until dxn. We will have to check that this is properly defined, because we defined it in a coordinate system using a chart. Obviously, we have to check that this is independent, the outcome of it is independent of the chart that we chose. And we have to show that it is non-zero, that it's really a volume form. So is it really non-zero? Yes, it is non-zero because the coefficient function here cannot be 0 because the determinant cannot be 0. Why is it that the determinant of G cannot be 0? Well, it's got to be invertible, right? We said it's not degenerate. So the fact that G is invertible, that the metric is not invertible, is not degenerate, that implies that we can define a volume form. Now, is it also well defined? In the sense that, is this definition chart independent? To see that, let us change the chart. You see, this will explain why we have here a square root. Why would we have a square root? No, why not to the 5th power or something? It's got to be a reason, and we will now see why the square root is needed. Here's the coefficient functions in the coordinate system x tilde. Here are the coefficient functions in the coordinate system x. And more precisely, just to be completely accurate, this is the way that the coordinate functions transform if we change bases in the cotangent spaces along with the change of coordinates. Right? If we go from coordinates x to coordinates x tilde, then we have a basis in the cotangent space dxi and a basis in the cotangent space after the change of coordinates of dx tilde I. If we perform that change of basis in the cotangent space, then this is the way that the coordinate functions transform. If we chose not to change the basis in the cotangent space, then that's gone. Okay? The coefficient functions stay the same. Okay, but we are changing the basis in the cotangent space along with the coordinate system, then this is the way that the coefficient functions transform. Let us write these out as matrices. That's a matrix, has 2 indices. That's a matrix with 2 indices. That's a matrix with 2 indices. In linear algebra language, this is to say, here we have a matrix, here we have a matrix, and this is the transpose, and this is the original change of coordinate matrix. This matrix is the product of 3 matrices. The determinant of that matrix is the product of the determinants of these 3 matrices, which is in particular the determinant of that matrix squared times the determinant of that matrix. Let's take the square root of that, and we obtain this. On the other hand, we also know how the n form is changing under change of coordinates, or more precisely, under the change of basis in the cotangent space that comes along with the change of coordinates. Namely, we pick up this determinant here. So this means that if we put these things together, see, what we found here is that the square root of g is transforming just exactly with that determinant, without the factor of 2, to take the square root. And that means that whether we write down the square root of the determinant times the n form in one coordinate system, or the square root of the determinant times the n form in the other coordinate system, it's the same thing, because we get this factor here from the change of the n form, and we get the inverse of that factor from the way that these coordinates change matrices enter in the transformation of that determinant, and therefore overall that's exactly the same differential form. So it doesn't matter in which coordinate system we defined it, it's well defined. Let's write it out explicitly. What are the coefficients of this volume form? Well, for that purpose, let's define the totally antisymmetric matrix epsilon in this way. I'm sure you've seen that before. The entries are plus if the sequence of the indices is an even permutation of 1, 2, 3, 4, 5, 6 until n. And the coefficients are -1 whenever the coefficient sequence is an odd permutation of the numbers from 1 to n. And if any one of those indices occurs at least twice, then it's 0, because it has to be totally antisymmetric. Well, this is our volume form. We can express the volume form also conveniently in this way. It's the square root of g times, here's the epsilon tensor that totally antisymmetrizes this. So if we sum all of these things, this is exactly what survives then. So in other words, the coefficients of the volume form, when written as a coefficient function in the tensor space, so if we view it as a tensor product rather than as a wedge product, then the coefficient functions are these. It's the square root of G times the epsilon tensor there. So what are other uses of G? The metric, I mean, there's no end to how much the metric will be used. This is just the start of it. In particular, turns out that in order to formulate the D'Alembert, and therefore also, keep in mind, in order to formulate, for example, the Klein-Gordon equation, we need a metric. You cannot write down a Klein-Gordon equation without specifying a metric first, because you cannot write down a D'Alembert. What's the difference between a Laplacian and a D'Alembert anyway? Well, they're really the same as far as differential geometry is concerned. It's just that when we're dealing with a Riemannian manifold, that is to say with a positive definite metric, then we call it a Laplacian. And when we are dealing with an indefinite metric, for example in general relativity, then we would call it a D'Alembert. So that's the physics terminology. Laplacian for Riemannian manifolds and D'Alembert for pseudo-Riemannian manifolds. But in mathematics, the tradition is to call them all just Laplacians. Okay, so how do we do that? How do we define this? We need a covariant definition of a second derivative operator that is not directional. The D'Alembert operator is not a directional derivative, right? So we need several steps for that. Here's the strategy. First, we use G, the metric, to give us a map between covariant and contravariant tensors. You've seen all of that before as lowering and raising of indices, but we use it for a particular purpose here. We use that to define the so-called Hodge star map, which maps R forms into n minus R forms. And that then defines a Hilbert space, or at least an inner product space of differential forms. With respect to that inner product, we can define the adjoint operator to the exterior derivative, and that will be the coderivative, which maps R forms into R minus 1 forms. And then the general definition of all Laplacians, of all D'Alembertians, is this. It's the anti-commutator of the exterior derivative and its coderivative. This is a beautiful formula because it gives you the D'Alembert operator or Laplace operator. We will always use the box, always with the D'Alembert notation, because what we really have in mind is, of course, general relativity with its indefinite metric. The point is, this will give us the D'Alembert operator much more general than you might be used to it. It's not just the D'Alembert operator on scalar functions. This is the D'Alembert operator also on one form. It's the D'Alembert operator on two forms, D'Alembert operator on n forms, right? On all forms. Because these are operators on all forms. So for example, the Klein-Gordon equation is then this. D'Alembert operator, namely this thing, plus m squared acting on phi equal to 0. The Dirac operator, by the way, can also be written in terms of the d and the del. It's just the sum of them. Okay, so let's pursue this strategy then, those 4 steps. Raising, lowering indices, Hodge star, coderivative, and then D'Alembertian. Okay, so first, covariant to contravariant tensor equivalence through G. So the metric tensor can be used as a map, namely by feeding it an argument into one of its available slots. It becomes a map from the contravariant into the covariant vectors. The metric maps contravariant vectors into covariant vectors. How that? Well, remember that the metric is a covariant 2 tensor. So you can feed it up to 2 vector fields. If you feed it 1 vector field, then you're still left with a covariant 1 tensor. And that's what this map is. Explicitly, if you take the metric, then it will map a tangent vector. This is a general formulation for a tangent vector field, really. See, this is just to make sure that you see the notation here. The EI of x is a basis vector in the tangent space dependent on x. For every x, we have a different basis vector. You can choose those basis vectors to be the d by dxi, but you don't have to. It could be any basis vectors in the tangent space. So this is a basis vector valued function of x, and eta I of x. And these are just coefficient functions. Okay, so each ei of x is a tangent vector, but these are just number valued functions, just coefficient functions. So this whole thing is a tangent vector field. And if you put this tangent vector field into one of the slots of the metric, doesn't matter which one because the metric is symmetric, then you get a covariant vector out of it. So here is the metric. Remember, this much is the metric. Coefficient function times basis in the cotangent space, tensor basis in the cotangent space. And then we feed this covector that vector, that contravariant vector. We put this tangent vector into this cotangent vector to give us a number. And what number would that be? Well, you see the theta is feeding on the EI to give us a Kronecker delta because they're dual bases. And this is just a coefficient function in front of it. It's linear. So we just have theta on the EI. That gives us a Kronecker delta. And then we have this psi I coefficient functions. So we carry forward the g mu of x here. We carry forward this coefficient function. It acquires the index nu now because that was a Kronecker delta, nu I. And we carry forward that basis vector that hasn't been used up yet. This is just coefficient functions, and that's a basis in the cotangent space. So overall, the metric has mapped a tangent vector into a cotangent vector here. And the coefficient functions went this way, that the coefficient function psi was mapped into the coefficient function g mu nu psi. G mu nu psi, which had these two indices contracted, and the nu was left over, and it used a lower index. Now, this is how it comes about that a tangent vector with an upper index gets mapped into a cotangent vector with a lower index. I'll only do that once, so in such a tedious way, but we have to go through it once just to make sure. Okay. And similarly, the G inverse tensor, the one which is twofold contravariant, does the opposite. It maps a cotangent vector into a tangent vector by exactly the same procedure. You know how this plays out. The index will be raised. Okay, so we can now lower and raise indices. For example, if we have a tensor with coefficient functions ti, j, k, then we can use the metric tensor, for example, to lower that index I just by contracting with the metric G. And similarly, we can raise indices. Again, as I said earlier, in principle, this is a different tensor than that one. But because the index was lowered by G, the convention is that we will still call it by the same name, T. See, if you had contracted with some other vector, with some other symmetric 2 tensor, for example, then there would be no reason to still call this T. It's just some other tensor. It's a convention to call them the same name if you raise and lower indices with G. Now, second part of the strategy to get to the D'Alembert and Laplace operators so that we can write down wave equations is to introduce the Hodge star map. I mean, we need the Hodge star map also for other things, not just for the wave equation, but this is the first real need for that. So we need a map which maps P forms into n minus P forms. So n is the dimension of the manifold. It maps P maps into n minus P maps. Well, consider a P form nu. Being a P form, it is in particular also a tensor, a covariant tensor of degree 0p. It's p-fold covariant. Which means that if you write it out in the tensor space, it has p lower indices. Now the trick is to raise those indices using G. What if we take this differential form and say, you've been constrained to be covariant long enough, now we make you contravariant, right? So we view the P form as a covariant tensor, and then we raise all of its indices using the metric so that it becomes a contravariant tensor of rank P0. And let's call that tensor nu tilde. So now we have a p-fold contravariant tensor, nu tilde. We will feed that p-fold contravariant tensor into the volume form. What do we obtain then? Remember, the volume form is an n form with a non-degenerate coefficient function, never zero. So it's totally antisymmetric covariant n-tensor. If we feed it that contravariant p-tensor, then p of the n slots are filled up, and n minus p slots are left over. But they will still be totally antisymmetric, which means that we are left with an n minus p form. So that's the method that the hot star is defined with. We take a p form, consider it to be a covariant tensor, raise its indices so that it becomes a contravariant tensor, then feed that object into the n form, which is the volume form, filling up p of its n slots, which leaves an n minus p form left over. And that is the star of nu. Nu is a p form, the star of nu is an n minus p form. You may wonder, what is that going to be good for? But we will see, it's very useful. You see, it's not really complicated. I mean, it's in practice a little tedious, but conceptually straightforward. So concretely, consider a p form. So here we have a basis in the space of n forms. We have the coefficient matrix, and for convenience, we put here a 1 over p factorial, so that later on we don't have a p factorial. So here we have coefficient functions times basis vectors. If we write this as a tensor, every differential form is also a covariant tensor, then we get that. You see, this is just getting rid of the p factorials because of all the antisymmetrizations here. So now we have taken our p form and we are viewing it as a covariant tensor. This is its coefficient matrix. Using the metric, we can raise all those indices. So we define now the nu tilde tensor, whose representation is the coefficient function with the raised indices and then the basis vectors in the tangent space, because it's a contravariant tensor now, this thing. It's just the same as our p form, just the indices raised. Raised using the metric. Now, we feed this contravariant this contravariant p tensor into the volume form. So we plug the nu tilde into the omega. Omega of nu tilde is given by, this is the coefficient function of the volume form. These are the coefficient functions of the of nu tilde. Then that gets contracted with the first p of those indices. And we obtain then the coefficient function here of the n minus p form, which is the star of nu. Here's the basis vectors that are left over. And okay, so that is explicitly what the star of a differential form is. So we can write the star of a differential form as the omega of the nu tilde, which is the nu with the raised indices, the star of the differential form can be written as a tensor product. It can be written using the tensor product as a covariant tensor, covariant n minus p tensor, but because it's antisymmetric, it's really a differential form. Here we have the basis of n minus p forms with this coefficient matrix. What if we did that twice? What if we applied the hot star operation once and then right away again? This is a natural question because the hot star maps p forms into n minus p forms. If you apply that again, then we find that hot star squared is mapping p forms into p forms. Is it the identity? It's not quite the identity. The proposition is, and I invite you to check that if you like. It's a little tedious though. The proposition is that if nu is a p form, then if you apply the hot star operation twice on it, you get another p form. In fact, you get nu again up to a prefactor that is either plus or minus 1. And it depends on what the dimension is of the manifold. And it depends on which degree of a differential form you consider, p. And it also depends on the signature of the metric. That's the difference between the number of plus ones and minus ones in the eta. So for space-time, that would be s equal 1. It's one time coordinate. Now, what was the purpose of defining that hot star? Well, with hot star, we can turn the space of differential forms into an inner product space. Assume beta is a p form and alpha is a p form. Then we define the inner product between this p form and that p form to be the following number. It's the number that you obtain when you integrate alpha, veg, star, beta. And now you see, now I can tell you why it was important that star was mapping p forms into n minus p forms. You see, if we wrote here alpha, veg, beta, and we wouldn't be able to integrate that over the manifold. Because if alpha is a p form and beta is a p form, well then alpha, veg, beta is a 2p form. But what's the guarantee that our manifold is 2p dimensional? This might work for some p, but in general it will not work. However, star of beta is an n minus p form. Therefore, a p form, veg, an n minus p form, is always an n form. And an n form can be integrated over an n-dimensional manifold. So therefore, we obtain with this definition an inner product for all p forms, from p equals 0 to n. Did you see that? So the star is mapping p forms into n minus p forms. Therefore, this is always an n form, which we can integrate over the manifold. And we obtain a number, and that's going to be the inner product. This is the definition for p forms, but we can choose any linear combination of 1 forms, 2 forms, 3 forms, etc. It's just an inner product, eventually, of the entire space of differential forms, turning it into an inner product space. However, is it a Hilbert space? Can we define a Hilbert space in this way? Well, that depends on whether or not alpha, alpha is always positive. It turns out we are not so lucky. In general relativity, it's not the case. And in general, you can prove that if and only if the metric is definite, then that inner product is definite. So on a Riemannian manifold, where the metric is positive definite, also this inner product is going to be positive definite, and therefore all lengths of vectors are positive, and then you can perform a completion of the space with respect to the topology induced by the notion of distance that comes from that inner product, and then you get a Hilbert space. But since the metric in general relativity is indefinite, we have that can be negative as well. So therefore, there will be vectors of negative length. There will be differential forms of negative length with respect to that inner product, where alpha comma alpha is something negative. So it's not a Hilbert space. But it's in any case an inner product space. Now, with respect to that inner product, we can define an adjoint operator for our exterior derivative, the so-called co-derivative. And once we have the co-derivative, we're almost done, because if you remember, the D'Alembert operator is just a combination of the d and the del. How do we define then the co-derivative? Well, it's the adjoint. It's the adjoint as adjoints are always defined, just from ordinary linear algebra or operator theory. So imagine that you have an operator which is mapping your inner product space into the inner product space. Technically, the operator has to be densely defined, so the completion of its domain has to be the entire inner product space. Then, what is the adjoint of this operator? Well, look at this equation here first. If you have a vector here, that's going to be a differential form, or a linear combination of differential forms of potentially even different degrees. So if you have a differential form here, differential form there, and you have an operator acting on the differential form z, and here's the inner product to be evaluated, in practice, this is going to be our exterior derivative d. So if you have an inner product like this and you have an operator there, the adjoint operator achieves the same inner product by acting on the left argument over here. So the adjoint operator is called A star, and it has to produce the same inner product as the A does here, but when acting on the left-hand side. So here's the technical definition of it. The domain of the adjoint operator is the set of all V in the inner product space for which there exists a W such that the V, AZ is equal to the W, which would be the output of the adjoint operator acting on the Z. These complications are only necessary when we really want to go into the functional analysis, where the domain of an operator is a non-trivial issue. In linear algebra, it never arises, because in linear algebra, your operators generally act on the entire vector space. But in infinite dimensions, that's a non-trivial thing. That's why one has to be more careful with the domains. But then, the definition of the co-derivative delta or del is that it is the adjoint of D, or technically the anti-adjoint, in the sense that it's the minus of it. So the co-derivative del is that operator which, when acting on the left here in the inner product space, produces the same outcome in the inner product as what the D achieves when acting on the right. Okay, you know that from ordinary quantum mechanics. If you take the adjoint operator, have it on a ket, the adjoint on a bra does what the original operator does on a ket. It's the same deal here, except that we defined a minus sign into this. You don't have to absolutely define this minus sign in there, but then it crops up later, and I will show you later where it comes up. It's the common definition to put the minus sign in there. Roughly speaking, it is because, if you remember, the Laplace operator is the second derivative operator, or in multiple dimensions, on flat space, it's the sum of the second derivative operators, right? That's what the Laplace operator is on flat space. Not quite, it's the minus of that. Because the sum of the second derivative operators is a negative operator. All its eigenvalues are negative. But in practice, we would like the Laplace operator to be a positive operator, so we put a minus sign in front. And that minus sign can be absorbed at that particular point here. Anyway, we'll see how that comes up. Okay, so what is the co-derivative, the co-differential del explicitly? This is how it's defined abstractly. And you notice we didn't need any coordinate systems for that. Well, what is it going to do? First of all, the co-derivative has to map p forms into p minus 1 forms. Why would that be so? You can tell by looking at this equation in the box. You see, if this is to be non-zero, and that is, let's say, a p form, then what is beta going to be? Well, beta will have to be a p minus 1 form, because d will turn it into a p form then. And we need to have p form, comma, p form to get something non-zero. So then we have here a p form and a p minus 1 form. So it's a p minus 1 form. So the del must take the alpha, which was a p form, into this thing, which is a p minus 1 form. So indeed, the co-derivative has to map p forms into p minus 1 forms. And the proposition is, and again, it's tedious to prove this, proposition is that the co-derivative maps differential form nu in this way. You take the nu, apply the hot star to it, then apply the exterior derivative to it, then apply the hot star to it, and then undo minus signs by putting this factor in front. And then that's what the co-derivative is. So strictly speaking, we don't even need to use a separate symbol for that. We could also use this and simply express the co-derivative in terms of the star and the d. But it's convenient to work with just the co-derivative. Now that you can prove from the equations that we had up earlier. It's not difficult. And you see some authors define the co-derivative as the negative of that, which means to have the positive up here. Let us collect, without proof, some of the properties of the co-derivative. Well, the square of it is equal to 0. How do we see that? We know that the square of d is 0. Now imagine you square that expression here. Forget about that stuff, that's just minuses. What you have is star d star, and if you do it again, another star d star. But the star squared is basically, up to a factor of minus 1, the identity. So you have a dd, which is 0. So that shows you that the co-derivative squared is 0 because the co-boundary operator squared is 0. What is it in coordinates? Well, it turns out that in coordinates, if you take the co-derivative of a differential form and you use the metric to write it as a contravariant tensor, then things are a little simpler. Then you can write it as this expression here. Again, follows from that up here. So you have to take the coefficient function of the tensor that you get from the differential form with all the indices lifted, and then you take the partial derivative with respect to k, do this contraction, divide for good measure another time with the square root of the absolute value of the determinant. That is what it is. And you see, this is, I hope, illustrating the value of defining things abstractly. Because what are you going to do with this? I mean, this is tedious, right? Why would it have to be this? But if you do it the abstract way as we did, then, well, the explicit form will come out whichever way it will come out, like this, and the properties will be clear. We can also prove, and that's again inherited from the properties of the exterior derivative of the co-boundary operator. If M is a contractible manifold, and it's also true in every part that is contractible of an otherwise non-contractible manifold, if M is a contractible manifold, then if a differential form is co-closed, then it is also co-exact. You see, if this was a D, then we would say that nu is closed. And if this was a D, we would say that nu is exact. And the same property holds for the coderivative here. It's really just via the inner product inherited from the D, from the exterior derivative. Remember that for an exterior derivative, for the D, for the coboundary operator, we had this theorem earlier, which said that if the manifold is contractible, then every closed differential form is also exact. Every differential form of which the D is 0 is the D of some other differential form. And here we see that it also applies for the coderivative. Some exercises prove these things. And the second exercise, well, I already gave it away. It was determine whether or not this is the derivation. It's not, but find out why. Now, before we get to the Klein-Gordon equation, let's use D and del to obtain the Maxwell equations. Let us define the field strength tensor. It has the electric field here on the first column in the first row, and it has the magnetic field in the middle with suitable minus signs. Then this is an antisymmetric 2 tensor. It's an antisymmetric covariant 2 tensor. We can write it in this form because it is actually a differential 2 form. The field strength tensor is a differential 2 form. We can also define a current 3 form. The electric current has charge density and current density. The 0 component would be the charge density, and then the 1, 2, 3 components are the current densities. And we can define them in this way, that we have here a vector, J mu, and the totally antisymmetric matrix. Here we have a basis in the space of 3 forms. So we have a 2 form, and here we have a 3 form by construction. We could also use the Hodge star and turn a 3 form into a 1 form, right? Because remember, the Hodge star is turning p forms into n minus p forms. For space-time, n is 4. Therefore, the Hodge star will turn 3 forms into 1 form, 1 forms into 3 forms, and 2 forms into 2 forms, for example, 0 forms into 4 forms. Anyway, we chose to write here the current 3 form, which using a Hodge star we can also turn into a current 1 form. Then the Maxwell equations are the following. And I'm putting that here out without proof. If you like, go through it and check that these equations really are the Maxwell equations that you've seen earlier. There is the Maxwell equation which says that df is equal to 0. Remember, f is a differential 2 form. And what this is saying is that the d of that differential 2 form is 0. In other words, it's saying that the field strength tensor is closed, is a closed form. Doesn't guarantee it's exact. Doesn't mean that f is the d of something else, but if space-time is contractible, then it does mean that. This difference, by the way, is captured in the so-called geometric phases, if you have heard of that. The Aharonov-Bohm phase, the Berry phase, geometric phases. That's exactly what happens when the manifold is not contractible. For example, if you have a solenoid in which technically you have a singularity of the fields, it's not defined there, and so it's not a contractible space, and then you can have that the f is closed, but because that has to hold, but it's not exact. There was a question, yes?
Is there something illuminating by using the 3 form rather than the 1 form?
No, not really. I could have, I'm getting to the inhomogeneous equations. We could have just defined the J, it's just that in the literature this is how it's defined. Okay, so just to close of the discussion of the homogeneous Maxwell equations, notice that the metric doesn't come into it. Because that's just the 2 form, and the d of it is a 3 form. It's 0. It says that it's a closed form. But the metric, I mean, even before we introduced the metric, we could have written down these so-called homogeneous Maxwell equations. Homogeneous because there's a 0 on the right-hand side. On the other hand, we also have the inhomogeneous Maxwell equations here. Here we have the co-derivative, right? Remember, that's basically star d star of f is equal to that. So the co-derivative is taking a 2 form into a 1 form. It lowers the degree of the differential form. So this better be a 1 form. And it is, because the j was a 3 form, so the star of it is a 1 form. You can also see how this is now dimension dependent. It would be a little different in other dimensions other than 4. And this depends on the metric. The metric goes into this, and the metric goes into that, because we have lowered and raised indices. The inhomogeneous Maxwell equations are sensitive to the metric. So f is assumed here to be an exact 2 form. I mean, not assumed. This is what the df is saying that f is a closed 2 form, and generally it is assumed that space-time is contractible, I mean, unless there are singularities in there. F is assumed to be contractible, which means that from the closeness of f, you can deduce that it has to be exact as well, which means that the f is the d of a 1 form. And this 1 form is also called the 4 potential, the electromagnetic 4 potential. Okay, so the field strength tensor is the d of an A. Locally, that's for sure always true. The question is whether it's globally true on the manifold that there's one A of which it is the D. We already discussed that because df is equal to 0, we have d squared of A is also is 0. Now, one calls the homogeneous Maxwell equations also structure equations. You see, this equation here, that d squared of A is equal to 0, which is this equation that df is equal to 0, express in a sense something trivial, right? If you know that in electromagnetism there is an electromagnetic 4 potential, then that equation is a given, right? It's trivial. It couldn't be different, because d squared is always 0, right? No matter what you apply it to, is always 0. So you can write down those equations, and they look non-trivial. They're the homogeneous Maxwell equations, but they are purely differential geometric in origin. They don't say anything about the physics per se, because it couldn't be any different. It's automatic. You may wonder, is that a speciality of electromagnetism? And it's not. It comes up in electromagnetism, but also in general relativity. In general relativity, too, there are so-called structure equations, or more generally, Bianchi identities. And they're equations that couldn't be different. They are imposed on us by the differential geometry. It's not a choice of any physicist to make. The math says that it couldn't be different. If you want to work with differential geometry, that's a given. Okay? So the homogeneous Maxwell equations are of this form, and we will also find such geometrically dictated equations in general relativity, so-called Bianchi identities. Now, the gauge principle of electrodynamics is simply the observation that if A is an electromagnetic 4 potential, therefore a 1 form, a differential 1 form, and A tilde is obtained by taking your electromagnetic 4 potential and add to it the D of some 0 form, so the D of some function, then this is your original 1 form plus another 1 form, but not just any arbitrary 1 form. You are adding the D of a 0 form. then the field strength tensor is going to be the same. Right? Because the field strength tensor is the d of A. The d of A is the same as the d of A tilde, because that addition won't make a difference for the field strength tensor, because it's the d squared of omega, d squared being 0. So that is another way of looking at the gauge principle. A and A tilde describe the same physics. They describe the same field strength tensor, because when you add to A only the d of a differential form, then that doesn't change the field strength tensor. Doesn't change the electric or the magnetic field. So f of dA is d of A tilde. Finally, we are ready to write down the Laplacian and D'Alembertians. The definition of the Laplacian, and remember, we are using here the mathematicians' terminology. The Laplacian is including the D'Alembertian. The Laplacian for an indefinite metric is called the D'Alembertian. So the formula that always holds is this one. The Laplacian is the anti-commutator of the exterior and the coderivative. And again, you could put a minus in there, but the way we defined it, this is a positive operator. If the manifold is a Riemannian manifold, if the metric is positive definite, then this is a positive definite operator. Remember that the Laplace operator is positive, but the D'Alembert operator is not. The D'Alembert operator has positive and negative eigenvalues. Right? I mean, if you think about it in Minkowski space, the D'Alembert operator, when your Fourier transform, is p naught squared minus p vector squared. Well, that could be positive or negative. The Laplace operator is just p vector squared. It's always positive when Fourier transform. So with this definition, what kind of operator do we get? Well, we get a second derivative operator, that's for sure, because the d is a first derivative operator, and the star and the del is also first derivative operator. Because if you remember, the del, the coderivative, is basically star d star. Now star is not differentiating, but the d is. So it's basically another d in there. So it's two derivatives. It's a second derivative operator. And this thing is lowering the degree of a differential form by 1. That's raising it by 1. So overall, it leaves the degree of a differential form the same. And here too, the degree of the differential form will be first raised by 1, then lowered by 1. So overall, the so-defined Laplace and D'Alembert operators are mapping p forms into p forms. And then in the case of space-time, where the signature S is 1, then this is also called the D'Alembert operator, and then we will write it with a box. Now, how does this work? As I advertised before, this is a great definition because it's coordinate system independent, and this thing acts on all p forms. It acts on 0 forms, like functions, but also you can act with it on 3 forms, 4 forms. You can write down equations of motions for those if you want. So in that regard, it's pretty nice. But how does it look like explicitly? Well, if you write this down explicitly, if you go through all the definitions and write out explicitly what it is in a coordinate system, then this is what you get. And you've probably seen this before if you've seen the triangular equation on curved space-time. So the D'Alembert operator acting on a function f, so we choose here to act on a 0 form, it's given by 1 over the square root of the absolute value of the determinant of the metric, times, and then here you have that square root of the metric term again, here the metric with upper indices, here the function once differentiated in the mu direction, and then the whole thing differentiated in the mu direction. And then you have the contraction over nu and mu. You may want to derive this. It's a little tedious, and later on we will see another way of deriving that. That is perhaps easier. But what you definitely should try to do is check how this reduces to the familiar formulation of the D'Alembert operator on Minkowski space in Cartesian coordinates. just plug in eta for G and see what happens. It really ought to reduce to this. So again, it's hard to motivate that sort of thing, but the abstract formulation, I hope, is clearer. So what are the properties of the D'Alembert in our Hilbert space of differential forms? Okay, so the D'Alembert maps, you see, I switched now to the notation of the D'Alembert, but it's equally the Laplacian. It maps R forms into R forms, and it does it in this way. It maps a new form, it maps the differential form nu into the action of del d plus d del on nu. And in the Hilbert space, or in the inner product space, I should say. It's only Hilbert space if we are working with a positive definite metric and therefore on a Riemannian manifold. What we have is that the D'Alembertian obeys this property. It is formally self-adjoint. If it is a Hilbert space, this is really self-adjointness. Otherwise, it's self-adjoint in an inner product space.
Is this the reason why you symmetrize the L and D?
Yes, exactly, because each one of them is not, right? But if you symmetrize them, then basically you get something Hermitian out of it. That's exactly right. So the D'Alembertian is self-adjoint with respect to the inner product space. Technically, in order to make it fully self-adjoint, let's say for a Riemannian manifold, we may have to choose boundary conditions. Just like when you look at the derivative operator on a finite interval, it only becomes self-adjoint after you've chosen suitable boundary conditions. And there may be choices of boundary conditions too. But if you choose boundary conditions, or if the Riemannian manifold is compact and let's say has no, or even if it's not compact, if it has no boundary conditions, then it will be self-adjoint. And even self-adjoint in the Hilbert space sense if what we're dealing with is a Hilbert space. Well, and then, yeah, I invite you to check, well, you gave it already away, why, how to check for it, that it is formally self-adjoint, simply using that the co-derivative is minus of the adjoint of D. You know, it's basically by just apply the dagger to them individually and symmetrization and so on. Just think about it a little bit and you will see how that works. Also, there are useful properties that the D'Alembert operator obeys, and it's too tedious to prove them all. Let me just list them. The D'Alembert operator commutes with the action of the Hodge star operator. That is not entirely trivial if you think about it, because the Hodge star operator has the metric in it, and the metric is space-time dependent. And this thing has derivatives, space and time derivatives. So it's not obvious why that would commute. But the way that the D'Alembert operator is constructed will guarantee that. Also, the D'Alembert operator commutes with the exterior derivative and with the co-derivative, basically because it's made out of them. Now, if we're dealing with the Riemannian manifold and the differential forms form a Hilbert space, then the Laplace or the Laplace operator is self-adjoint in the Hilbert space sense, which means that the spectral theorem applies, which means that the Laplace operator can be diagonalized, and it has a real spectrum. And for Riemannian manifolds, the spectrum of the Laplace operator is actually always positive. For compact Riemannian manifolds without boundary, let's say. You know, it can go negative if you have funny boundary conditions. If the Riemannian manifold is also compact, has a finite volume, then it turns out that the spectrum is also discrete. I will get to that later in the course. The fact that the spectrum of the Laplacian is discrete, one moment please, opens up an interesting possibility. You see, if you know the spectrum of the manifold, then if you know the spectrum of the Laplace operator on the manifold, then you know how it would sound if you took a spoon to it and made it ring. Okay, because the Laplace operator, or the D'Alembert, goes into the wave equation. And the eigenfrequencies of an object that has the shape of the manifold are exactly given by that spectrum. If you have a finite size object, it will have a discrete set of eigenmodes and of eigenfrequencies. And clearly, if you change the shape, it will change the eigenfrequencies. And then one can ask, if I know the eigenfrequencies, can I calculate what the shape is? This would be effectively a Fourier transform of geometry. You're not Fourier transforming functions now, you're Fourier transforming curvature. You're Fourier transforming the shape of a manifold itself. Can you hear the shape of a manifold? You had a question?
I remember taking a course similar to this stuff. We used Dirac operators, but we had the problem of like trying to figure out if it had a continuous spectrum or a residual spectrum. Are you going to show that in like later on in the course that those don't exist in this case, or because you're saying it's discrete, so the residual and the continuous would have to be 0, right?
Yes, it's a pure point spectrum. Technically, it's a pure point spectrum. Yeah. Exactly. Yes, no, we won't prove that. But I'm just saying that if the manifold is a compact Riemannian manifold without boundaries, then there is a theorem that says that the spectrum is a purely point spectrum, so all the points are separated. In fact, there's not even accumulation points, except at infinity.
So if we don't have a compact, we'll get those extra spectrums?
Yes, you could. Yes. Okay, so the spectrum of a Laplacian can carry information about the manifold, and we will consider the question, how much information does it contain about the manifold? In fact, there exists a mathematical discipline which is older than quantum mechanics, older than general relativity. It's called spectral geometry. It goes back to Hermann Weyl, 1904, I think. And he asked the question, well, how much can we tell about the shape of an object from the sound it makes when you make it ring? And it turns out you can tell a lot, and there are certain circumstances when you can tell actually what the shape is of a manifold on the basis of that. I will say much more about this in later lectures, but for now let me just point out that this question is mathematically intriguing because the question how much the spectrum of a Laplace operator is connected to the shape, the metric of a manifold, is directly connecting the mathematics of quantum mechanics to the mathematics of general relativity. You see, it's connecting functional analysis, the spectrum of an operator, to the metric of a differentiable manifold. There are very few instances, can't even think of, well, yeah, there are a few other instances where functional analysis is deeply connected to differential geometry. The language of quantum mechanics is connected to the language of general relativity, and that's one of those instances, right? So we will pursue this a little bit further, how the spectrum of a manifold indicates the shape of it. So now we are ready to define the Klein-Gordon action, because we have the D'Alembert operator, and we will also see how the D'Alembert operator arises in a natural way from physical actions. Consider the action of a Klein-Gordon field. It's 1/2 integral over the manifold, and then it's this. You may know it in this formulation. It's G mu nu, the coefficient matrix, and then partial derivative of phi in the new direction, for partial derivative of phi in the new direction. And here you have the volume form. And explicitly what's going on is written here in black, just to remind you of the tensorial structure of all of this. This really is, of course, a covariant 2 tensor. And that really is a tangent vector acting on a field. Here we have a tangent vector on a field. All of this is indicated here, and you feed that into your metric, and that's how you end up with a scalar. It's just too tedious to write it out all the time. So I just wrote it up one more time. And later on, we will just work with the coefficient functions. But really, what's behind all of this is abstract structure, where we have an abstract tensor that's being fed abstract tangent vectors or cotangent vectors. And we arrive at this form on the basis of Einstein's equivalence principle. Namely, in special relativity, this equation holds with the eta here. In general relativity, by Einstein's equivalence principle, that equation must hold with G. And at every point on the manifold, there's a coordinate system such that the G is the eta, so that we have the usual Klein-Gordon action in the neighborhood. Okay, if we spell all of this out, then we have the G mu nu of x, we have the partial derivatives over here, partial derivatives over there, and this volume form is the square root of G dnx. Now, from this we get the D'Alembert quite straightforwardly. We integrate by parts. So here, this is just ordinary derivatives, right? You may already know about covariant derivatives, but this is just ordinary derivatives. So now we integrate by parts. But what happens if we integrate by part? If we integrate, let's say, this thing by part, then the derivative no longer acts. I mean, we get a boundary term that will be assumed to vanish. And we get that this derivative no longer acts on the phi, but the derivative acts on everything else. The derivative acts on this, it acts on that, and on this. Okay? And we get a minus sign from the integration by parts. And so what we get is 1/2 carried forward, and then we have the phi, which is the one that's no longer being differentiated. And this derivative is now acting on everything else. It's acting on the square root of G, it's acting on the G mu nu, it's acting on the other partner there. And we also put here a 1 over square root of G times the square root of G, just so that this becomes the volume form again. And then we can collect all of these things together, and we say that this operator here is the D'Alembert operator. And that's the D'Alembert operator that we also saw earlier to arise from d del plus del d when applied to zero forms. That's exactly the same way. So you see how this structure arises naturally from an action. And that's the last slide. So the Klein-Gordon wave equation is then obtained in this way. If you remember, you take the Lagrangian, differentiate with respect to phi, and that's equal to d by dx mu, dl by d phi by dx mu. Here our Lagrangian function is this. We just wrote down what the D'Alembertian is explicitly. This is this, is this. And so plugging it into the Euler-Lagrange equation, we obtain the Klein-Gordon equation is simply that the D'Alembertian acting on phi is equal to 0. If we had put a mass term in there, it would have shown up here in a natural way, of course, as well. Which physical fields are described by Klein-Gordon, by the Klein-Gordon theory? Well, there are basically 3 that come to mind. There are meson fields. They're consisting of quark-antiquarks. Quark-antiquark pairs are behaving like scalar fields, can behave like scalar fields, and that would be meson fields, but they're not fundamental because they're made out of more fundamental quarks. Then there's the Higgs field that has been confirmed in the past few years, and it is probably not composite. It's probably a fundamental scalar field that obeys the Klein-Gordon equation. But we don't know yet. There are still people hanging on to the idea that the Higgs might be composed of more fundamental things. And then there's the inflaton field, which of course will concern us later on in this course. It's a scalar field that is assumed to have played a huge role in cosmology. It has a tremendously large mass, which means that we can't produce the inflaton field's particles in the lab. There's no way, it's many orders of magnitude away from what can be done at CERN, probably. I'm not so sure. But at the tremendous energies available shortly after the Big Bang, the inflaton field would have been a dominant thing, actually. There's something special about scalar fields that we will later find out why the inflaton field is so important in cosmology. And that, what is so special about it is that the potential of an inflaton field, we haven't put a potential in there yet, but it would be very easy to do. What is very special about scalar fields is that their potential acts in the Einstein equation later on exactly the same way that a cosmological constant does. And the cosmological constant makes the universe blow up exponentially. Other fields don't do that. Electromagnetism, for example, or fermionic fields don't do that. So that's very special. There is still a remote, perhaps, but still a possibility that the inflaton field might be the Higgs field, but it requires some fine-tuning. We don't know that yet. It would be conceptually very efficient, of course, if that were the case. Okay, that's it for today.